Hi, good afternoon, all. Thanks for joining this session in a quite early on time, and thanks a lot for making it up. We shall start the session at 5 p.m. So until then, kindly just wait on the line. If you have anything in the meantime, you can always drop details there on the chat box. No, I think in the meantime, just everybody is here, and there are more people to join in for the session. So we would like to know, what interests you to participate in the program, and maybe just let us know your interest, maybe your motivation to attend the session, so that I could possibly direct the session more towards those meaningful requirements, and that becomes more interesting for you too. Uh, so kindly just drop in the messages in the chat box and let us know maybe where you're from, and what background of engineering are you from, if you're from engineering background. So depending upon the number of participants on various areas like electronics or electrical or mechanical, I can possibly kind of boil down a few discussions to emphasize on those areas. So yeah, please drop in some of your information on the chat box so that we can have a better sessions today. I'm just waiting for your inputs on the chat boxes. Okay. For the few things here, for people have asked for. Um, okay, will you provide the presentation after the session? Ramnathan, the presentation has a hard copy, a soft copy we don't provide as such, but yeah, you could have the videos available because this is a free session. The videos are available, will be available in Decibel's website. If you purchase the course, it will be available in your login. You can take up the course. You can always see the video part of it. So interesting to know mechanical engineering. Good Rishabh from mechanical. All right. I'm interested in embedded programming, and I'm from electrical background, working in modeling and simulation in MATLAB. Very interesting, Ramanathan. Automotive engineering, electrical, mechanical, simulation of power distribution requirements wise for vehicle level. Okay. All right. Automotive design, aesthetics. That's really interesting, Sunny. Power electronics. Okay. Amit Navichandran. All right. Good, good, good. BTech electrical. Okay, that sounds like almost it's a combination of multiple areas, majorly emphasized on, I think, the mechanical, electrical, electronics. And interesting, there is a Chris from computer science. Right. Aerospace. Um, okay, that's quite a catchy tag. I wish things goes on well for you, Jigme. How EV vehicle works. I think, yeah, that's a very wide discussion we could do, Nathan. Maybe the topic is today on modeling and simulation. I'll possibly restrict myself on those areas. Ankit Das in Zoom attending from mechanical. Sabadeep, electrical, renewable. Wow, that's really interesting. Very cool. Mechanical engineering, student of friends interested in looking to modeling and simulation. Automotive engineer, Yashwant from Hyderabad, MTech in power systems. Very interesting. That's good to know all of your background in mechanical, automotive, electrical, some are from aerospace. Thanks a lot. Thanks a lot for introducing yourself and being a wonderful audience and interacting. So for the people who are on the Zoom, so a small request, if you have any issues on attending, hearing, or seeing the videos on Zoom, you can always join us on YouTube Live. It's much more, I would say, advanced streaming platform. So you can even just go back and watch if something was paused at a minute and things like that. So just confirming with a couple of people here, is my audio, is my voice audible for you? And is my screen visible for all of you? I'm just trying to switch a screen and trying to see if you can see the screen, which is not static, so that we could start ahead the session at sharp 5. Maybe just one or two people. Could you please just confirm yes or no? Okay, thanks a lot. Thanks a lot. LA, Sanju. Okay, fantastic. Looks good. I think we're all set to take ahead the session. For today, we could be starting at 5 or 5:01 sharply. I believe you have been receiving emails, I think, without an issue. Cool. Let me go back and look through some of the chats on the YouTube simulation. Okay. Anup from Sweden, electronics engineer, enter better battery systems. Um, wow. Okay. Learn University, automotive, electrical. Thanks a lot, everybody, to introduce yourself on these details here. So I think we should be starting a session in a minute. So in the meantime, I'll just go through a few more chat boxes. Background doing masters in electric mobility. That's really interesting to know, Chaitanya. Where do you picking up your masters in electric mobility, Chaitanya? Aerospace engineering, advanced diploma. Okay. BE, PhD in electrical. That's great. All right. Quality. Amazing. I'm really thankful for all of you to attend this session and being really interactive and introducing yourself. I really appreciate. So let's go ahead and start the session because it's 5, and we promised to start the session at 5. Um, so just give us a second here. We should be good enough to start the session going ahead. All right. Good evening, everyone. Welcome to the session on EV modeling and simulation fundamentals as a part of the 2 hours course today. It's a privilege to host you, all the people who joined here, and it's been a fantastic number of participants, number of registrations we have got for today's session. It's close than 1,600 people. Really impressed by a number of people who want to learn about EV systems and seriously. And it's glad for us from Decibels to host these free courses and bring our expertise and industry knowledge to share across to these platforms. And thanks a lot for joining in, by the way. Uh, let's go ahead and start the session. So I will be the person who's Suraj, will be your course director, and today's person who would be delivering the session on the EV modeling and simulation. This is a course flow, what we have for the session. We would start with the EV powertrain subsystems. So it's a content. We cover what subsystems are in electric vehicle. Why I'm covering if the session is about simulation, because only when we know what subsystems are there, it becomes more meaningful to understand the simulation and the importance of simulation on these subsystems. That is why we would, have discussion on powertrain subsystems for first 15-20 minutes. I think people who have participated already in the past courses on webinar may have already learned these things, but yeah, we want to bring everybody onto a same platform uh, uh, as we go ahead with the discussions and the simulations too. Then we jump into why we perform simulations. And I'll go very deeper in showcasing a few of the areas of the powertrain sizing calculations. Also the influence of certain parameters such as motors, uh, such as your drive cycle, vehicle weight, and so many other parameters, and also parameters such as atmosphere and how it influences the simulation, and why we need to do a simulation to uh, do the sizing of components and things like that. We allow a small break for 10 minutes because we understand that it is quite difficult to have attention more than 45 minutes. Uh, so we would take a small break there, and we would start back the session. We would showcase on the hand calculations because it will be very tough to engage everybody onto the calculations. So I'll just showcase a step-by-step approach on how do we do our calculations. And also, we will demonstrate the model which we have built for Ather 450 with the software called Scilab, which will give you sort of an overview on how actually we build simulations and things like that. That's the pretty much of a flow. So we account for close to 2 hours of a session with a small break. And we will take a QA definitely later on. And I'll try to take a QA on the break timings too. If you have any questions, like you could just drop in there and kindly hold on. So we should be able to take ahead those questions. I'll try my best to answer them because there are a lot of participants. I'm not sure if we could address everybody, but I'll definitely try my best to answer as much as possible. Yeah. So the small request, I think we almost logged out with Zoom on the number of people. So kindly join on the YouTube Live if somebody is yet to join, or if your friends are joining in, please inform them to join on the YouTube Live. So this would be me, who is the presenter and the course delivery person for today and the speaker for today's session. So that's me, Suraj. With my background in industry, I worked for 8+ years. I'm a graduate in mechanical engineering. I worked for a company called ITC Infotech. Through ITC Infotech, I had a pretty much a privilege to work on projects for Mercedes-Benz. And I worked for a company called Fisher Dynamics. So then I worked for a couple of other projects in Fiat Chrysler. So apart from it, I like teaching. So with all the experience in the knowledge industry, we thought, why don't we set up a company to share the knowledge relevant from the industry side. So that's what we've been doing. So we train a lot of people across the places. So going ahead, I just want to confirm that if my voice is audible for everybody, because there are a couple of comments that they're not able to hear my voice. before I start ahead, let's not have a blindfold conversation. So maybe one or two people can confirm me if the audio is good enough to go ahead. All right. So looks good. Looks good. Thanks a lot. So yeah, a little bit about decibels. So decibels have different divisions of operations and verticals of operations in industry. We consult a few of the startups in India, and also we consult a few of the startup part of Europe and Sweden. That's one of our business line. And we also consult for new product development and manufacturing sector. With a lot of consultants we have in-house and also contracted. We set up certain lab facilities in colleges and also at industries uh, do to do testing of components of EV and many other things. So as we have that background of industry, we also teach certain courses through lms.decibelslab.com. So that's where you've been logged into the courses and got to know about the courses. So we connect all the places into a place from academy and industry. Then the people from industry asked to provide certain engineers trained in EV. So we provide those services of employment to engineers at some of the partner industries too. So without taking too much time over there, let's move ahead and start the technical session. So I'll start this part with EV subsystems as we're discussing in the session planning. So let's understand what are the components are there in the electric vehicle system. So we would start ahead the system with the motor and the transmission. So right, so we have a motor and transmission, which we call as a drivetrain in electric vehicles. So we had IC engines before, so we replaced the IC engine as a component of motor, right? And then we had transmission. So we had like a 5-speed, 6-speed, 7-speed, 8-speed transmission, but those transmissions are also coming very small. We are anticipating to have like 2-speed transmissions or now 3-speed transmissions, or companies like Porsche has also come up with some transmissions, which is a planetary gauge system. So we would not have a big transmission in electric vehicle, but we'll have a smaller transmission. But if you ask me, the transmission will be still there majorly in electric vehicles. That way, if you talk about four-wheeler segment, it is definitely will be there because we needed final drive, drive gear ratios for the differential and things like that. So the transmission is required. We can discuss about more on why do we need a transmission and what is the advantage of having a transmission. Then we have a motor. So there are multiple types of motor with respect to different technologies, which is there in the industry. So most of the motors which we use in automotive applications will be AC motors and of their own sizes and the complexities into our place. So as a replacement for the IC engine, so we have a motor and then we have a transmission, which was there, but it is more simplified right now. We also have a hub motor, but we'll not talk more about them as of today's discussion. So on the other side, to control this motor, so we need an inverter, right? So it's also called as a motor controller. So the functionality of a motor controller is this, which because we have a DC, which is at the battery, right? So the battery is a DC source. So we take the DC, but motors are AC. So we need to convert the DC to AC. So that's one of the functionality, converting DC to AC. And also we need to ensure that the control of motor speed, motor torque, a lot of other algorithms in terms of requirement in automotive is done through motor controller. So it's a complex power electronics and embedded system device which engages to ensure that the motor performances are always met with respect to the very specific requirements as such. So then we have a battery pack itself, which sits right somewhere here, which are having like a cells, and then cells are built into modules, and modules are built into a battery pack as such. So it's quite a lot of chemistry background into a place, and also the integration of cells, and also into the modules and thermal management system are a whole proper mechanical design of the components into the battery pack itself. So then we have battery management system, which is a state-of-art electronics, which engages to ensure the safety for the cell and safety for the pack, because lithium-ion cells are susceptible to certain conditions to catch a fire and many of those situations. So because we also store a lot of energy within the cell, so it becomes very challenging to ensure the cells are always safer. So we use battery management system to ensure the safety for the battery pack and cell level and a lot of other things. And also apart from it, the battery management system does function to to monitor a lot of parameters in the battery pack, and also it does certain, what I say, predictions of SOC and SOH algorithms, and also it does a lot of the things on SOE and various different information. And also it does communicate with the vehicle to inform the driver, okay, what is the battery left and how much you can travel and things like that. That all the computation is done in battery management system. But we also see today that the state of art today's system have like machine learning algorithms to inside the battery management system that they're constantly able to learn through the data which is being generated at the sensors and all the components in the vehicle itself. We'll talk more on that going down the line. So then we have onboard chargers, which is a component which helps us to charge the battery pack. So because we have an AC supply at our wall sockets powered by any of the grid suppliers. So we need to have an onboard charger, which basically converts the AC to DC and then give it to the battery pack to charge the battery itself. I believe you got that understanding right. And then you have DC-DC converter. The DC-DC converter is a device because we are talking about higher voltages in the battery pack, maybe starting at 48 volts up till 850 volts architecture we have in commercial vehicles. If we talk about bus and truck application, we are talking about 850 volt applications. And we're talking about passenger cars, like even people have been able to go up like 400, 450 volts also. And maybe there are some applications they have even gone more than that. The challenge is because all your auxiliary systems, like the headlights, taillights, horn indicator, maybe the dashboard, instrument cluster, all of them work at not at very high volt. They typically require 12 volt architecture. If it is a passenger car segment, they require 24 volt architecture. If it is a commercial vehicle segment, like a trucks or any of those systems as such. So when we have the 12 volt architecture or 24 volt architecture, but we have like higher voltages, maybe like 350 volt. So we need to step it down and give it to the auxiliary systems. So that's why we have a DC-DC converter, which steps down the voltage from the battery pack and gives it to all the other peripheral systems. So apart from it, we have a heater, which is slash cooler, we can also call it as. The functionality of a heater or a cooler is to ensure that the battery pack temperature is always kept pretty much at the same value. Or a range of certain temperature, so that the battery performs as best as possible. As you might have aware that the battery is susceptible to temperature. If there is a small variation in temperature, the cell energy and the output of what a cell can give out will drastically reduce, and it affects the life of the cell and in a long time. There are a lot of problems with temperature to a battery pack. So we need to ensure that that there's always the battery pack is kept at a specific temperature. That is done by a heater or the cooler. So if the temperature is higher, the cooler turns on and it cools down the battery pack. If the temperature is lower, let's say like countries like US or somewhere in other parts of the world, so the temperature is lesser than a specific operating battery temperature, then we would use the heating system to heat the battery pack. So sometimes we cool the battery pack, we also heat the battery pack. So we need to also understand that there is energy required to heat and cool the battery pack. That energy is also consumed by the battery itself. Then we have an air conditioning system, which is here. That ensures about, because in the IC engines we have IC engine driving the compressor, which is a air conditioning system, right? So we don't have that engine running. So now we need to again have a motor, auxiliary motor possible to run the air compressor. We need to again take the power from the battery pack itself. So when we have that requirement into our place, why I'm discussing all these things is we are trying to calculate, okay, what is the battery size required, right? So what is the component sizing required? What are the peripheral systems required? So when we have to do that, we need to understand all the systems into our place so that we can calculate what is the load on this system. Then we will be able to figure out, okay, how the system transiently behave. That's the reason I'm trying to brief out all the components. Then in the next further slides, we can go deeper and understand. So here are some points. And if you have any questions till here, I can take few questions and move on to the next part of the presentation. So yeah, there are a few questions. I'll try to be a little louder for the rest of the session. How do we estimate instantaneous power demand in electrical vehicle? Amit will definitely go ahead and learn that part of it. How do we estimate? I'll showcase the things. Insulation heater is used. What is optimal temperature of the battery pack should be maintained? It is very specific, the cell, Sabrish. With respect to specific cell chemistry you're using, there's a defined operating temperature region which is best for the cell. So we need to look for the data sheet, and then we should be able to retain that temperatures for the required systems as such. So some more questions here. What is the difference between a quick charge and a normal charger? Okay, so is there any other communication protocol used in EV other than CAN? So let's majorly we use CAN because it's very stable communication, and because we need that to ensure uninterrupted data losses into a place at any given moment. So CAN has been proved out as a tech, so we typically use CAN majorly, same as in EVs too. How is the power variance needed in is handled? We can definitely discuss ahead down the line on this. How schematic changes in heavy machinery? I think it's pretty much the same as a requirement, but majorly the size of the components would possibly vary, and packaging of the components would possibly vary. Right. So a few more questions. What is optimal temperature? Okay. Okay, so let's go ahead on the next part of the discussion. So I'll definitely touch base on the questions which possibly I am not able to do now. So as such, of a drivetrain, we call it in electric vehicles. So we call a transmission and the motor together, we would call as a drivetrain in electric vehicles. So which we have seen in the last images on the presentation. We have seen the motor and the battery pack, sorry, motor and the transmission integrated together. You could see the live image, which is here, which is from Audi e-tron. So how the motor and the transmissions are integrated together, and we call that as a drivetrain all into a place. So if you see here, we still have to retain the transmission, but it is not very big and bulky, but it is very small of its size. I will quickly run through a few slides here, so that gives an emphasis on all the components which we're trying to discuss. I'll not touch base on the motor technology because that is not a point of discussion in this session. So I'll touch base more on the requirement of the simulation side. So if you see here, why we need to consider certain parameters of the motor in simulation. So one thing, we have a data sheet, and from the data sheet I've taken some graphs here, which says that it's a peak torque, then there's a continuous torque, and then there's a peak power, and there's a continuous power. And also on the other side, on the right side, it says about the efficiency of the motor. So the motor have varied efficiency at a given places, depending upon the point of its operation. The objective of an engineer in the area of electric motors in the EV's requirement would be to ensure that the motor always operates as best as possible. So we had a lot of challenges in ensuring these requirements, but we do it with various different control methods, and also to have certain transmission requirements into our place. So why do we have to have these information into a place? Because the motor is continuously operating with respect to varied speed and a load. When it is operating at a varied speed and a load, it is going through all the places. If you could see here on the bottom image, which I've tried to put across, which is having that the operations of a motor, operation of the motor is all over its efficiency places. Are the green lines, which is over there, which is actually the movement of the vehicle speed with respect to motor speed with respect to the varying the motor efficiencies. So it means that the motor is operating at a various points, and the efficiency of the motor is also varying with respect to different loads and different RPM. So the idea here, which I'm putting here on these images, I'll describe in the further slides, that because today motors were there from 100 years, but the thing is, in the last 5 to 6 years, for the traction application, the motor technology has been improved very drastically into the various scales. The one of the major factor in motor technology is improving the efficiency of the motor, and also reducing the size as such as a requirement. Because in automotive, if the motor is very big and bulky, the weight is more, and then again, end of the day, the motor has to give the torque to push the whole vehicle system as a mass, and also need to draw a current from the battery pack. So if you want to have a very big system, and that again doesn't make any right choice to keep it to the automotive requirement. That's why people are working extensively to ensure that the motor efficiencies are always higher. That's a one side, and the second side is also the energy density. It means that having a smaller motor, but it gives highest amount of power and torque at a given requirements into our place. That has been an extensive area of work, how people have been working in the areas of motor. The major requirement of the motor is because now if you take a motor for any application, like an application like automation, or an application something like which is used in the water pumps, those requirements are very specific to a set value. Possibly you don't have a huge variations of a motor operating speed or a motor operating load. But if you take it to automotive application, the motor is continuously varying with respect to a given time. How does it vary? Let's say you want to start a vehicle, you want to accelerate a vehicle, so you press the accelerator. The motor has to produce a lot of torque and bring up the vehicle to a specific required speed. And you drive it in the highway, you drive it in the traffic condition, the roads are not flat. It means that the motor is undergoing a continuous transit requirements. So when we're going through all these transit requirements, it means that it is not operating at a one point, it is operating continuously at varying points. That's been a complex challenge in automotive, to have the motor to work specifically for automotive application, right? And that's one of the challenge. The second challenge is when you use a motor for an application like automation, or even for the borewell application, typically we would have a very specific temperature, or let's say a bandwidth of temperature which is not drastically varying. But when we talk about automotive application, then today you're using the motor, let's say a vehicle in Bangalore, possibly tomorrow using at Chennai or any other places, where you're subjecting the motor to undergo a lot of variation with respect to atmospheric temperature. So that is another challenge. And also there is atmospheric conditions as such as many different ways. So it means that is a very big challenge to have a motor for a tractive application as a design of system all in place. But considering that, why we're talking about these graphs here, I'll introduce you the graphs in the further slides, where we can discuss more about considering what efficiencies and how we model these systems into a place to take a right values. Transmission EVs. So it's a very interesting topic. A lot of people would say that we don't need a transmission in EVs because motor itself has enough torque. But definitely it is not the way, because if you want to keep a motor directly onto the vehicle, so the motor becomes very big and bulky. That becomes a very big challenge to ensure a packaging requirements. So we would definitely need a transmission, but the transmission will not be very big as a size, but it will be very smaller, which is as showcased in the image, which belongs to the Aether of 450's bike. So we have a very simple transmission than having a complicated CVT mechanisms and things like that in electric vehicles. So why do we need a transmission into a place? Because if you want to directly plug the motor to a wheel, the torque requirements will be very, very big. It means that the motor also becomes very big, and the motor becomes bigger, the size of the motor increases, and the weight of the motor increases, and also the current drawn by the motor, all this parameter will get affected. So having a transmission would give us two leverages to optimize the motor size and also to optimize the motor operating points, which is typically shown in the image here. So where you could have a rightly sized transmission by having a right gear ratio, so you can actually ensure the motor operations to be optimally placed at highest efficiency region. So, and when you do that, it becomes very optimal, and the efficiency of the system goes really, really higher. And that's why we have transmissions in automotive. So then we have inverter. So the functionality of an inverter is pretty simple, as we're discussing in the past, but it's a state-of-art electronics again into a place, which ensures the conversion of DC to AC, and also in times of a requirement of a regenerative braking. So we also convert the electricity produced by the motor as a generator unit to another sources, as such as the batteries too. So the major functionality would be convert to DC to AC that we can supply to the motor, and also it engages the control of the motor in various different ways. If you see on the right side, we can see the emphasis on the image, which tells about the efficiency of operation. I kept the image, which is motor plus inverter efficiencies, but let's talk about only the efficiency. This motor control is also undergoing certain efficiency regions. The efficiency is not always constant. It means the efficiency is continuously varying with respect to certain parameters, possibly with respect to motor RPM, the motor current. Again, the same way the inverter efficiencies are also continuously varying. Then we talk about the chargers. Typically on the powertrain sizing, we don't consider chargers as one of the parameter, but on the overall vehicle level, we also consider chargers for modeling. They're the devices which helps us in charging the battery pack, which you see here. There are a lot of conversion happening from AC to DC. Now we're talking about a vehicle to grid and grid to vehicle, things like that. So we also need to have like a bidirectional converters. So there is again conversion losses which have been happening at these systems. As such as a powertrain sizing, we don't consider EV chargers for the modeling requirements. But at a vehicle level, if you want to consider, we would also consider the EV chargers also to model in the powertrain systems. So the traction cell as a part of it, which you could see here, we have arranged the cell and then the module and the concept of a battery pack all into a place. Here I have some characteristics on the battery pack itself, which talks about, I would say, the cell itself. So it means that the cell characteristics are drastically affected by various situations. The meaning of that is if the temperature of the cell is varied, then the cell behaves in a very different way. If the current drawn from the cell is different at a given moment, obviously it will be different in automotive because it's a transit requirement. It means that the cell behaves continuously different in various load conditions, temperature conditions, depending upon its age, the number of cycles it has gone through, the way we have abused the cell. It behaves in various different circumstances with respect to how it has been used into a place. So why we're talking about all these things is because if we do not understand these systems, we won't be able to visualize why simulations are required, and that's the purpose of having and going through this slides into a place. So then the battery management system, which is a set of electronics which helps us to ensure the battery is always safer and which is always kept within its limits and then safer operating areas into a place. So keeping all these things into a place, now that is a very overview of all the subsystems in EV. The reason why I was trying to put across all these systems with the graphs as on efficiency side of it and on also its variation side of it is to understand how the system is varying with respect to given minute, and how simulation will help us to account all these points to analyze and make a very analytical reason to size the components into our place. So my question here on the screen is, why do we need to model EV powertrain, right? So that's the question. So I would be leaving a couple of seconds here for the floor to answer a few questions. I've gone through a few of the slides. I've gone through like few documentation which I shared it across. So why do we need to actually model the EV powertrain? What would be the very important purpose of modeling the EV powertrain? So open for questions. You can always drop in some of your answers here. Reduction of pollution. Would there be increase in efficiency by using EV planetary gas set? Okay, so economically appreciated model, maybe for the performance, weight distribution, predict model performance comparedness requirements. Very interesting. So good to know all of your insights on how and why we need to model the system. It saves a lot of money and time. Definitely true. It get optimum solutions. Which type of cells efficient in EV? Great. Space. Okay, very interesting. So I'll go one by one, and I'll try to brief you through on my information about the system and why do we model electric vehicle powertrain for any of the requirements. If you see here, I've just gone through overall picture of all the calculation purposes in electric vehicle powertrain. As part of it, on the leftmost side, we have a drive cycle. On the rightmost side, we have a battery pack, we have a motor, and all these things. So this is a whole journey which is trying to show us from the point that we start from the drive cycle, and then we could end up possibly at a battery sizing and a motor sizing. This is a journey which we all go through to do any of the simulations or also to perform any of the activities about sizing the components, which we see here on the leftmost side as a drive cycle. And we have some standard drive cycle. such as a FTP75. We also have drive cycles like WLTP cycle. It means that we are feeding the vehicle. The y-axis is basically the vehicle velocity, and the x-axis is the time. So the vehicle's velocity is continuously varying with respect to time, and the drive cycle represents the driving pattern of any person, or it's a driving pattern which is used for, I would say, the testing requirements and also the simulation requirements. So these drive cycles are standard. And how do you put a drive cycle? These drive cycles are defined by considering a lot of data, which you generally drive around the city conditions and things like that. So they have certain information about the way we drive. So we use these drive cycles to calculate the amount of the motor power and a motor torque and a battery pack size and all these parameters into a place. So where our journey starts in simulation, the journey starts from the drive cycle data, which is shown in this side of it. There are many different methods to also do that, but one of the method which I'm trying to focus is on this method. So which is, we start from the drive cycle where we get the data of the vehicle speed with respect to time. And now you have a continuously, if you see here, it's a dynamic system, right? So it means that the vehicle speed is continuously varying with respect to time. And also the vehicle is like accelerating, decelerating, all these things are happening on the vehicle itself. When the customer is pressing an accelerator, there is the vehicle speed is increasing. Imagine if there is a up, what I say, gradient forces. The road is inclined, so then there are different forces acting on it. So it means that from the vehicle drive cycle, we are able to get all this data, and we feed that data to the next level, where we will be able to calculate a rolling resistance, aerodynamic resistance, acceleration forces, grade forces. We will calculate these forces which are acting on the vehicle to meet the requirements of a vehicle speed. With respect to vehicle speed, what are the forces acting in the vehicle? We will be able to calculate using these data, which is here on the resistive forces. So now we know the vehicle speed. Now we know the forces acting on the vehicle, and we will know the tire diameter. So by knowing the tire diameter, we can calculate if the vehicle has to go at a very specific speed, then what would be the RPM of the wheel we can calculate. That is in the top of the screen, which is here. So we start at this point first, and then we calculate these values. If you see here that the vehicle velocity is given from the drive cycle, right? And the acceleration also requires to be fed because of from the drive cycle itself. A rolling resistance and the grid resistance will not be depending upon the vehicle speed because they're independent of the vehicle speed. Then with this data which we have, we will be able to calculate, with this data we can calculate the wheel torque because we know the tire diameter, we know the forces acting on the vehicle. If we do the math, we will be able to calculate a wheel torque. Then we know the vehicle speed here because of the velocity, and we also know the tire diameter. By having that math, we are able to connect the wheel speed. So how are we able to do that? We have a data of the drive cycle. From this data, we are able to calculate the forces, and also we are able to calculate the torque with these forces because we know the tire diameter. The other side, because we know the vehicle speed, we are able to take the data and we'll be able to calculate the wheel speed. So now we have wheel speed and the wheel torque. And now the next point is the transmission. So the transmission has certain gear ratios, right? So those gear ratios we will model inside the transmission. And also the transmission have a varying efficiencies. That efficiency also will be able to model within the transmission model itself. So by having this model, we will be able to calculate the motor speed which is required which should be delivered by the motor, and also the motor torque should be delivered by the motor for any transit requirements. So somebody was asking a requirement from the data, right? Like, how do we account for transit requirements? So this is a way we will be able to model whole powertrain system, and we will be able to calculate the transit requirement of the motor and transit requirement of the motor speed and the motor torque. So that's the way we would have the data of the motor. And by this data, we will be able to calculate the motor power. That would be one of the very valuable input for us. And we can also calculate the motor current. And typically, because the voltage of the motor is like the selection of the motor voltage is typically fixed. From there, we can calculate the currents and all. We can calculate also the motor positive power, which is to drive the vehicle, and also the motor power that we can do a regeneration. The regeneration, which you might have aware about it, the motor can act as a generator during the braking conditions. At that time, the motor also produces an electricity. So we can account how much positive power we require to drive the vehicle and how much actually the power we can produce by the motor during the regenerative braking. Because we have a data of the drive cycle, right? When the vehicle is decelerating, it means it is coming the negative side of the graph. So we are able to account all this information. I'll show you the graphs and show the further presentations. And we're able to calculate the motor power, which is a positive power, which is required to drive the vehicle. And also we can calculate the regen power, which is basically the power which is required, which power that can be generated with respect to the drive cycle too. And with this data, we will feed it to the inverter, because the inverter would be the device which actually like drives the motor, right? So we are trying to go in the reverse way, and here we will account for losses in the inverter. Let's say the motor power comes 10 kilowatt, but there will be some losses at the inverter too, and we need to account those losses also, and then we will pass on those information to the battery. At the battery, we have a designed battery pack, and where we know what is the cell capacity, what kind of cell we are selecting, what is the cell voltage which will be there. And with all this information, we will be able to calculate the certain parameters such as SOC, that is state of charge of the battery pack, depth of discharge of the battery pack, what is the battery power itself is required, what is the pack current which is required, what is the cell C rating required. And we can also calculate the temperature of the battery pack at a given moment of time, because you know how much of current you're drawing. You can have a model where you can optimize to understand with respect to this current drawn, what would be the temperature increase at the cell itself. And then you can calculate what is the temperature of the battery pack will be increased by given drive cycles and things like that. So this is a very step-by-step approach which anybody takes to actually calculate uh, the powertrain sizing of any of the requirements. So we start from the drive cycle, because we have a drive cycle where we get to know what would be the vehicle's demands, and then from there we could build a whole model, and we will be able to account for our powertrain sizing calculations. This is a typical approach of what we would take. Now I'll go to our next phase, and where I'll be able to brief out the importance of all these subsystems into a place. Okay. So first is why we need to model it, because if you understand all this dynamic system which you have undergone, because the system is continuously varying with respect to time. It means that the vehicle speed is varying continuously because of the drive cycle, and not just because of drive cycle, the way we drive the vehicle, because we have a varied vehicle speeds at a given moment of time. So that's why the vehicle speed is continuously varying, and the road conditions are different, because sometimes we have uphill, downhill condition. There is a hump. There is a traffic signal. There are so many parameters, right? So which also need to be accounted when we are trying to do a sizing calculations. Then on the last one, which would be the driver demands. So the driver demands is a requirement where we need to also understand how we want to accelerate a vehicle, or how we want to get a driving requirements for our own conditions. So it means that the whole system itself is undergoing a dynamic change at a given moment of time. So it means that we cannot be able to calculate this with the hand calculations, and also we won't be able to account certain parameters. So that is why we would need a simulation, and by only doing the simulation, we were able to account a lot of parameters into the consideration, and we'll be able to get a very accurate results when we talk about sizing of the components as such. And going to the next slide, which is here, study the influence of parameters. This is a very important parameter, the functionality why we perform simulations. The first thing, which is the motor efficiency. Let's talk very deeper here about the technical requirements. So when we have a varied motor efficiency, which we are discussing the presentations on the motor point, right? The motor has continuously, like the efficiency of the motor is continuously varied with respect to the load and the RPM of the motor. And also the efficiency of the motor also changes with respect to the temperature of the motor, which means that we need to account these parameters, because if we want to do a hand calculations, it becomes quite impossible to just actually calculate the motor torque outside, like the motor power required as a vehicle level requirements, which means that we need to embed these continuously varying, because the vehicle speed is continuously varying. With respect to that, the wheel speed is varying, and the wheel torque is varying, and then we have a transmission, and then that is coming to the motor torque and a motor speed. So it means that the motor speed and the motor torque are continuously varying. because the continuous with respect to those operation, the motor efficiency is also continuously varying. So we need to account those efficiencies. That's one of the very primary parameter. And if you do not account that, what happens? Imagine the motor efficiency is, let's say, 10% lesser. When it is 10% lesser, it means it is drawing too much of current out of the motor controller. And again, motor controller is trying to draw a current from the battery pack. It means that you're trying to draw more current for the vehicle requirements and to achieve the driver demands. When we're doing that, basically you're trying to discharge more battery. When you're trying to discharge more battery, obviously the battery SOC goes down. And you could tell to the customer that vehicle will come for 100 kilometers for a single charge. But without rightly accounting the efficiency of the motor with respect to varying points, then possibly the vehicle will only come for 80 kilometers. Right? So it means that the motor efficiency has to be accounted, and it becomes very, very typical characteristic to study the overall power requirements of the vehicle if you want to understand very deeper. And the second thing is the motor efficiency also varies with respect to temperature. So we also need to model the system in such a way that, okay, we can check how the motor temperature is going to vary with respect to varying operations of the motor, with respect to RPM and torque and things like that. So by considering these data, if we include all this information into the model, then the model will become more accurate to predict what would be the motor current, what would be the motor power, and then we can actually account exact amount of energy required by the whole vehicle to drive in the real-time conditions. Then again, the inverter efficiency is also not constant. It is continuously varying with respect to the motor speeds and also the motor current requirements. So when we are doing that, we would need to include these efficiencies also. If we do not include these efficiencies, as we are discussing, it will impact on the overall vehicle range. It means that the vehicle range will be completely different when we drive the vehicle in the reality. But we would have thought, okay, the vehicle will definitely give 100 kilometers, but it will be giving like 85 or 80 kilometers of a range into a place. Then the transmission efficiency, and apart from the transmission efficiency, also the transmission gives out a very a valuable opportunity to vary the motor speeds at a given time, that we can keep the motor always operating in the sweet spots. And by doing that, you're getting a higher efficiency at a system level. And transmission efficiency also varies continuously because it is not always constant. Maybe the values will be very smaller, but again, the efficiency of the transmission continuously varies. We need to include all these parameters into the efficiency in the model itself, that our model becomes more accurate when you're performing all the calculations. Then the fourth point would be the influence of temperature. As we're discussing, the cell will behave varily, with respect to the temperature of the battery pack. If the battery pack temperature is drastically high, then the power output by battery will be definitely reduced, and also the amount of energy that is given out by the battery will be also reduced. So we need to consider that parameter as well when we're trying to model a whole electric vehicle powertrain. And how do we do that? As we're discussing in the previous model, we know what are the current drawn at a given time by the battery pack. We could do a modeling by knowing what are the losses in the battery pack, maybe IR losses and all these things. Then we can account how much is the temperature that can be generated at the battery pack. So when we know exact data of the cell, how the cell behaves with respect to a specific requirement, then we will be able to include that parameter of the cell temperature, and then study how the battery will behave with respect to given requirements. Then the HVAC system, because HVAC system is again the load on the vehicle, on the battery pack. So it is drawing a lot of current. So we need to include that. Maybe over a span of, let's say, 100 kilometers of a driving, you're using the air conditioning system for, let's say, an X amount of time. So you're drawing a certain amount of current to run the motor. That's basically to run the compressor. So we need to account those parameters also. So typically we talk about automotive passenger car segments. We're talking about like 2 kilowatt up to 3 kilowatt applications of an air conditioning system. Talking about a truck like bus segments and all, we're talking about a 10 kilowatt or a 12 kilowatt application. It means that if you're running the air conditioning system for 1 hour, you're consuming close to 2 kilowatt of the battery pack. It means it's a lot of energy that has been consumed to run this air conditioning system. So then on the next one, the battery cooling and heating. Why we should consider battery cooling and heating? Because how do we need to heat the battery pack? If you want to heat the battery pack, you need energy to heat the battery pack. So it means that energy is again coming from the battery pack itself. So to heat the liquids or even to cool down the liquids into a place. So we would account all of that, and then the motor cooling and heating, because it's a very important parameter, because a motor is highly susceptible to temperature. If you operate the motor above its certain operating temperatures, the efficiency of the motor drastically goes down. We discussed above that if the efficiency of the motor drops down, it is going to affect the overall system continuously into a place. So we need to ensure that the motor cooling, and also the, I would not say that heating is a wrong word over there. It's only the cooling as a part of it. The motor cooling is required. We don't reheat the motor. I'm really sorry. Apologies on that. So the motor heat cooling is required at a given requirement. So again, to cool the motor, we need energy, which is again consumed for the battery pack. We would account that power requirements too, and influence of atmospheric condition. It's a very, very important parameter on understanding that why we study the influence of temperature, because we discussed that the motor efficiency varies with respect to temperature as one of the parameter, and also the battery behavior is continuously varying with respect to the temperature. So imagine you're driving the vehicle in Bangalore. Maybe the optimal temperature in Bangalore is somewhere between like 25 degrees Celsius to, let's say, 34 degrees Celsius nowadays. So it means that the temperature of operating is pretty decent. And if we take the vehicle to any hotter regions, maybe like up north or any of the places where the temperature is really high today, it means that the the same battery and the motor is operating at a higher temperatures now. So the ambient temperatures are higher, and then that impacts the battery pack really, really a lot. So we need to understand and study these influences also on the battery pack and also on the motor, because if you're operating a vehicle at a higher temperatures, it means that you need extensive cooling of your battery pack and also extensive cooling on the motors too. That it means that it will require energy. That energy again comes from the battery pack itself. So this is how the whole parameters. There could be a lot of other parameters also. Like if you talk about DC-DC converter, so now we have to supply energy to headlights, tail lights, and infotainment system, and there is a navigation system running in. So where do we produce the energy for these systems? Again, we have to give the energy from the battery pack itself. So we need to account some losses on the DC-DC converter, and then again we need to consider what is the load is there on the whole vehicle itself, and then we can study all the parameters. So by considering all these parameters, now if you want to imagine, is it really going to be possible that you can do a hand calculations and you will be able to perform a calculation the way that I can include all these parameters. I can tell, okay, what would be the exact requirement of the battery size, or this is how the cooling system requires, and all these things. So it is quite impossible to do hand calculations, and even if we can try, it becomes quite a challenging thing, because if there is a small variation which you have to do, it becomes a very daunting efforts to do that. So that is why we use simulation tools. That majorly use simulation tool in the industry today is MATLAB. And apart from MATLAB, there's a one more tool, IGP CarMaker, which people also use. And people have been using Ricardo. I think there's a specific workbench. I think Ignite is a workbench, I believe, from Ricardo. So there are a couple of softwares like this, which has been used for the powertrain modeling. To include all these parameters and then study how the system really behaves, and what would be the requirement of the system at a given moment of time. Because today what we're talking is just not about a vehicle design, because today any mature company is definitely talking about a system level efficiency, because we know everybody can build an electric vehicle. It is not big challenge that, okay, you could just go to a couple of vendors and select the components, and let's say you can build an electric vehicle. But where is the competitive advantage? Like how Tesla has a competitive advantage today, their drivetrain system efficiency is so high. It means that they have optimized the whole vehicle components to a very best size, that the system efficiency is really, really high. How they done it? They would have done it by studying the parameters of each system and the influence of the system to a very, very next degree of understandings. The same way today in any industry, we're talking today any automotive vehicle manufacturer, we're just not talking about integrating a system. We're talking to ensure that the lowest amount of energy consumed to drive the vehicle for a 1 kilometer. If you take a vehicle, like if you take a two different vehicles like Tesla and another vehicle, what Tesla can consume for a 1 kilometer drive range, if you compare a same vehicle of a same segment, Tesla beats everybody odd out. It means that it is having a highest level of system efficiency. How do we do a math? You can just do the math by knowing the battery pack size and the range of the vehicle. If you do that, then you could get typical energy consumption per kilometer. If you do it for a couple of vehicles, you could check out how best what Tesla has been doing, because they could do that by understanding the systems to a very higher level. And that's what my interest, to share the insights on the areas of simulation and modeling, because that's how much simulation is important in a given any given time. By having a right simulation data, you would be able to predict the system behavior in a right way. With all this information, with all the efforts we're trying to put till to the last slide, what we're trying to achieve is to calculate the motor torque, so that we can tell to a motor manufacturer that, okay, hey, I need a motor of this big size. Like, let's say in terms of its torque, in terms of its operating RPMs. Maybe we can also define, okay, this is a bandwidth of operation I'm going to operate my motor higher. So I want a best efficiency in these regions of the motor, and motor power and things like that. So that becomes a very crucial thing as a part of this, which is here. By performing simulations, we are able to get all these values on the motor side. On the battery pack size, because we included all the parameters, we can actually study and tell that, okay, this is the exact size of the battery pack which I require. Imagine if you do a small mistake and wrongly studying certain parameter which is not included. Let's say the temperature of the battery pack is not included, and then we did not consider about cooling of the battery pack. Then when the temperatures are very high, let's say on the winter region, the vehicle may give exact same mileage. But during the summers, now we need to cool the battery pack because the temperature is really hot. The cooling system is consuming energy to cool the battery pack. So that becomes a very important factor when we are doing the modeling. So by having a right data of the model, by including all the parameters at the model level, we are able to calculate the exact motor power which is required. And by knowing the motor power, we can actually calculate the number of cells in series, number of cells in parallel, and even by having the data of current, which is a pack current, and then we go to a cell C ratings and all these things, we will be able to choose what specific type of a cell I can buy from a manufacturer, right? Because for your application, let's say you're building a sports car or a racing car, not a general, a cell will be applicable for your requirements. You have to buy a cell which actually discharges really high, and it still retains its integrity at those higher discharges too. So if you're using a vehicle for a truck application, then if you're using a cell for a passenger car segment, if you're using a cell for a scooter segment, it is very specific. So that is only possible when we do a simulation studies. We can detailedly check what is the cell discharge current at a given moment of time, and by knowing the exact discharge current, we can choose the right cell. And by choosing the right cell, like, you're saving a whole lot of a big thing for a company, because if something goes on a wrong cell selection, it affects very badly for the whole company, because it's not a small thing. It becomes a huge efforts in once you decide a cell and then move on to the next pack design and then all the things into a further on place. So by doing the simulation, we are able to exactly study this is the way the cell currents are going to behave. And if the cell currents are going to behave this way, I can choose this cell, or I can put this number of cells in parallel, that the pack currents are always within this limits and things like that. So that's how we can do it. This is what we call as a sizing of the components. We are able to define motor torque, motor RPM, motor power. We can give it to a motor manufacturer, hey, I need a motor of this requirements. Then you do with the simulation data you have done. So you were able to go to a pack manufacturer, and we're going to tell that, hey, this is my current which is coming at the cell, and this is the pack level currents, and this is the battery pack power requirements at a given moment of time. And I want you guys to work on this the battery pack development. And then the pack manufacturers like Ion Energy or Exicom, even Bosch, Conti, or all these people, they will take that data. Maybe this data is given from OEM, and they will be able to check, okay, what would be the temperature of the battery pack at a given time? How do I study the influence of atmospheric conditions about the battery pack? And any of those things are always done, and then we select a cell. Then we'll be able to select the pack size. We will be able to select the thermal management systems. All these things become a progressive efforts, in understanding what is this. component selection is all about at a cell level or a pack level into a place. Then apart from it, because we know what is the current drawn by the motor and what is the current given out from the battery pack, we know all the parameters at any given moment of time because of the simulation data. I'll show the model how exactly we'll be able to study and execute. There we'll be able to check what would be the conductor selection, maybe even the thickness of the cable to carry a specific amount of current, and all the studies, and also maybe the transit current at a given moment of time can be also checked with the motor model, the vehicle model data we are trying to build it into a place. Then there are small components like contactor. It's not a contact, it's a contactor selection. So the contactor components or any of the other subsystem, maybe you want to select the right fuse, any component which comes as a part of the whole vehicle, that will be decided by doing the simulation, and the simulation will give us that insights to choose upon these things. And that's why if you want to decide the component sizing, the first and foremost point is to design and develop a whole system in a simulation software, and study all of that to decide these components. And the last slide on this part of the presentation is to understand about optimizing and predicting. And now we know this is how much is all required, and this is how my battery pack is be there, and all these requirements are there. But the most important parameter in any automotive requirements today, if people are talking about, is to actually optimize the systems to ensure, okay, maybe in optimization state, I can give you the example here on the image which tell about the regenerative energy. So by knowing a drive cycle, you're able to implement the drive cycle. You know what would be the negative torques, and then you can account them into the motor, and you know the motor efficiencies. And in the regenerative region, because motor has different efficiencies, when it is doing a region, we can implement those efficiencies also, and then we can actually calculate how much would be the regenerative energy I can produce. So when you account that, the whole battery pack size will definitely become different, right? So it is not the same size of the battery pack, because you're able to actually produce some amount of energy during the region and store that energy back into the battery pack. So that is becoming a very a good approach in optimizing the system, because by doing that, we can tell, okay, your vehicle can give you more range. Maybe without having a region, possibly the vehicle can give 100 kilometers. By knowing the region and exactly controlling certain parameters, we can tell, okay, maybe the vehicle can give 110 kilometers. So it has increased the range of the vehicle by 10 kilometers. Again, I'm just giving a rough figures. But if you study the system properly, we could optimize in such a way that we can include and make the vehicle much better. And also by this data of the region, we can check, okay, what would be the current that can be generated at the regions. And by that way, we can know whether our cell, which is there in the battery pack, can actually get charged, because cell will have a limitation of charging and discharging. So there's a specific definition given by a cell manufacturer. So we will definitely know by knowing because when they suddenly break, there is a large amount of current which has been generated at a motor, and we may not be able to use all of that current. And if we try to do that, then the battery will go bad, because the battery cannot charge that faster. So it means that there is a lot of understanding by studying this system, and that is where we talk about optimizing a whole system into a place. And that is where we talk about motor operating points, and we could tune the transmission as best as possible, that motor always tends to operate at our best regions. By having a model in the simulation software like a MATLAB or a Scilab or any of this system, you can vary between these transmission gear ratios. You can optimize and check, okay, whether my vehicle is giving an output, but where the motor is operating. If you're able to make a motor to operate, let's say even 5% efficient in the overall range of 100 kilometers, you're able to get 5 kilometers more. It means that just because of the proper system design, the whole system is behaving exactly the way you want it to behave, and you're making the system to provide its service for a longer time too. And that's an advantage, having a right transmission and tuning those transmissions. It would be very easier to do that by changing the gear ratios at your let's say at a model, and study, okay, how much would be the effect of by changing the one small teeth and things like that. Optimize the pack size, because as I said, by including a parameter like a region, you can actually optimize the size. You can make a pack smaller, and so that it still gives you 100 kilometers of range. And maybe on the other side, we could make it in a very organized way with respect to packaging size and all these things. We can reduce the mass of the battery pack by knowing exactly what cell C ratings we're going to require, and depending upon it, we can select a right cell, and that actually optimizes the whole battery pack design itself. And maybe by selecting a right cell, you could even reduce the thermal requirements if it's a two-wheeler applications and other stuffs. So overall powertrain optimization. Now, what we kind of trying to see through here is it is all interlinked. If the motor is bad at its efficiencies, then the inverter is bad at its efficiencies, and the battery pack is going to die faster. And also, like, if the cell is going to degrade over the lifespan, and then the energies which is available at a cell is also going to go down, and the power is going to go down, then again it affects the performance of the battery pack. It is an overall system all into a place. We need to consider everything and optimize it as best as possible, and that is where we would do these studies, and that is where the importance of the simulation is there, that we could make it as best as possible without even having a vehicle itself. And by having the right data, which is given by a motor manufacturer, which is given by a traction inverter manufacturer or a cell manufacturer, all these people, and knowing exactly the way the vehicle behaves, knowing what type of losses will be there in the vehicle. There are certain losses like we can call inertial rotation losses. They're like accounts for 2% of the vehicle losses. So by knowing exactly these values, we can actually make a simulation model to a very good extent, and study the system as best as possible, that it will give us exact data of what we want as a motor size, battery size, optimally at every point, that it becomes a very matured product, and it becomes actually a very matured vehicle into our place. And this is why we go through all these data and simulation models. And that's what I was trying to bring in my first part of the presentation, to emphasize more and more on why the simulation is required. Because I know somebody can just use a MATLAB and the models are available. If you guys just go to MathWorks, you can just click on the model and then you can download the model, you can see the model. But actually, until and unless we don't know the importance of each system and contribution of the each system to the vehicle level, then there won't be excitement and importance to study and to get deeper into those subjects. And as such, as an automotive, as I was telling, today everybody talking about efficiencies, because we had motors, we know what efficiencies it were. Today we're talking about 96, 97% efficiency for motors at very of the specific motors into a industry of automotive. It means motors were there, but we are pushing as much as possible to get the best efficiencies. The inverters were there, but we're trying to put as much as technology into a place to improve their efficiencies. Every system, we're trying to push their limit to achieve the best of efficiencies. Moment we do everything optimal, the energy consumption becomes lesser and lesser. And at an overall way, if you visualize, the battery pack gives lesser energy. It means you can get a more mileage, and you can have a smaller battery pack but a longer range. That solves the problem of range requirements in electric vehicle. But this is one part of it. But on the other side, imagine, because the system is highly optimal, it is consuming lesser energy to drive. It means that it is consuming lesser energy to get charged also. And we know the charge and electricity come from different sources, like maybe it's a thermal power stations and things like that. So it will still produce lesser emissions. So this is a way how we need to think overall life cycle. The small effort we are trying to put to improvise inverter efficiency is just improving so much onto your environmental emissions also. And that's why we can optimize systems, and they can improvise the whole vehicle powertrain by doing the simulations. So there are a lot of questions. I would take those questions now. I know it would be a lot of questions, but I'll try to address. But don't feel bad. We would try to have all these charts, at our as a list when we end the meeting. I'll try to see if I can answer these questions, maybe coming live on YouTube sometime. But for sure, I would not be able to answer something which is not about simulation, because something not on simulation can be addressed in other courses as well. So let's take a few questions. This would be the break time. Let's say we're at 6:05 now. We can take another 10 minutes. That's till 6:15. So if you have any questions, you can ask me here in the meantime. But until then, you can take a break. If For the people who have dropped their questions here, I'll try to answer them. Okay, so one by one. What can be affect energy consumption? Okay. Okay. So I'll go by one. A current generated is AC, but to charge. Wow. So please drop in any of the questions you have. So then maybe just copy paste the questions which you had in the past. That would be easier because there are so many chat boxes. It is quite difficult to like go all the way up and try to figure out. So we will start back the session at 6:15. So people want to take a break. You can take a break for just like other 9 minutes ahead. What electrical drive we use in EV? Um, so they, as we discussing in the beginning, so there are typical PM motors are the major ones, which have been trying to use for EV applications. For uh, all the AC, the headlights stuff, auxiliary battery pack, right, which powers this. So Ashish, even though there's an auxiliary battery pack which powers this, but how do you recharge the auxiliary battery pack? So can we regenerate when we are using a BLDC motor? Yes, and then we can do that. Then so it's a capability of your motor controller also that it can do a regen or not. Which software is better for simulation? As I said, it's always MATLAB has been really good. Apart from MATLAB, people also using other tools, which is Ricardo, Ignite, and also other tools like IGP CarMaker. Uh, what is CAN? CAN is control area network. It's a communication protocol. Is there something called global drive cycle, or we are not advised to buy EV which is designed for United States? I would not say like it is like suggested, but they would have considered certainly um, parameters and would have designed the vehicle to operate. But if you ask me, for the Indian conditions, because we have very bonkers temperatures, and things can definitely get affected. Because there was a case, even if you study, go back, and it's available on the internet. The Nissan Leaf vehicle, which has been sold in US, two different states, where the temperature of the state is really, really high, it is giving like 30 kilometers lesser range than the just next neighboring state. It means that, yeah, you could see really how it is affecting. Scilab Simulink Xcos is generally preferred. Yeah, Xcos Scilab is a free software, which is we also teach in our advanced courses, which is an advance of this course. You can definitely participate there and take it up. Depends on type of simulation, how much power alternator generates. It depends upon the capabilities of motor braking and things like that. Why lithium ion batteries are used? Because of their energy density and the volumetric energy density and specific energy density and volumetric energy density. And they store the energy without losses for a more number of cycles. Self-discharging is very lesser. That's why. For efficiency, can energy efficiency motor be replaced by conventional motors in use in EV? Sorry, I didn't understand, Salish. Okay, so I'll take some more questions here on the Zoom. Is there any specified limit which shall be incorporated to regenerative power? I mean, there is a threshold. Yes, Anil, it is definitely there because the battery pack may not be able to take as much as regen we can generate. So there is a challenge. How can impact on the rolling resistance and the gradient resistance? So gradient resistance, as you know, Madhusudan, it's like mass into GVW into sine theta. So like because you need to overcome the grade. So obviously you have mass, which will definitely impact to overcome the grade. Which test is used to plot torque speed profiles? Okay, that's on the testing side. What different methods to model the motor apart from mathematical modeling? Uh, as of now, which we have encountered, most of the motor models, we do it in many different softwares. As a vehicle level, we don't typically like model the motor as a very specific requirement. We would take some blocks and we will put those constants and try to see for the powertrain sizing as a requirement. But the motor design itself is a very different way. How can I plot? How can I plot this for my project? That would be a very specific question, Ritesh, we can discuss sometime. Why DC-DC converter is used? I was trying to explain that. Glycol coolant is used in electric vehicle battery. DC-DC converter is used. Okay. For a step down, what is the effect of energy consumption of battery if the motor torque and speed points used instead of entire plot as input? You will not be able to exactly get the right values of the current requirements. That's what it happens. How can I plot my vehicle driving cycle? There are a lot of apps available. There are a lot of instruments available, Ritesh. You can buy them and keep it on your vehicle. You should be able to plot them also. How to rectify the exploded of batteries in EV? Oh, that's safety systems. Which preferred cooling? It depends upon the system requirement, right? If it's air cooling or liquid cooling. How to measure instantaneous power? I was telling you about it. How we can model and get it. Can you tell about battery life? That would be, maybe you can take another session on the cell modeling itself, Yashwant. I'll be able to tell about it. What different methods to model the motor apart from mathematical model? In case of efficiency in EV by using full trigger system. Yeah, there are good chances, Shubham. Even Porsche has done it by using certain things. How can I connect subsystems like driving cycle, motor, and battery in a Simulink model? It's a very technical question. Maybe I don't know how I can answer everything here, but yeah, you could actually do that by doing certain connections between the systems. Can we charge the battery using wheel rotation in bike? Okay, if we right, so that's pretty much. I think I've tried to answer all the questions here in the chat box. As I said, ambient complete performance is dependent on ambient temperature. So the energy, so there is a chance that changing the complete design of vehicle based on location. Now, when we need to study the system, how it can actually get affected. So let's say you're designing a vehicle and you know this is you're going to operate in hotter temperatures. Then you need to have a cooling system. It means that, okay, whether the cooling system should be there or not can be decided. Cooling system will work or not work for a specific need can be defined with respect to its where it is operated. It is not possible the vehicle design itself is different. Majorly, overall, it will be similar, but system can be very specific. How should I begin learn this domain? Like step to go ahead from very basic since I'm first year student. Himanshu, maybe you can connect back to us. I'll share my contact. You should be able to get guidances. How to select a specific battery and a motor as they mutually depend on each other and so on. That's what we're trying to do, Vimal. We're trying to build a simulation model and we're trying to decide upon how we can do all these things. Okay, so I would go back to chat box. I'll try to see how best I could try to answer. There are various different methods, Sampath, to do the speed control. Um, are the resources available in simulation in MATLAB Simulink? Harshit, definitely there would be a lot of data available. What if we use DC motor instead of AC? Can we use supercapacitors? There are people trying to use supercapacitors also. But yeah, you need to study it, how much it can impact and affect. Why do we need two contactors? It depends upon the system integration, Ashish. What efficiency of the component selection suggesting what would be cost of the can we can a EV be operated at F1 at 1 feet height of water level? All right. So I think good questions here. I'll try to answer as much as them. So which typical DC converters are used? I'm not from actually the power electronics department. I can just check and come back to you. What kind of topologies are used in DC converters? What performance analysis for torque versus speed of the DC motors? All right. So, hi, Bharat, you there? Yeah, just give us a minute here. We should be able to start the demonstration of the electric vehicle powertrain model, which we have built. So I believe it will give you sort of a more idea on actually the way the whole powertrain is modeled. We'll try to showcase that the whole design itself as the way we have done it in the software. So to do that, I would invite our simulation engineer, uh, Mr. Bharat. Um, Bharat, will you be able to share your screen and showcase the whole model to us? Right. So I believe you all can see the screen, which is shared by Bharat. Give us a second here. I'll just check. Please do confirm if you're able to see the screen, and then we should be able to take ahead our discussions in other minute. We shall start the session in just a minute, please. All right, I think, yeah, let's get started back. So about the whole discussion which we're trying to do it here. Okay, so that I believe I'm audible back. So yeah, we have a screen here which is visible to all of you, which is the model of the electric vehicle powertrain, which we have built that we could demonstrate on the screen. Yeah, like the way we have used a simulation software, which is called Scilab. Okay, it's why we have used Scilab, because it's a open source and it's a free software which is available for anyone. You can go ahead and download it, just like 200 MB file, and that becomes very easier for you to install in very simple softwares and simple laptops and things like that. Okay, so that would be the purpose. We are also trying to help you out, that you can also build the simulation model and things like that. So we have a course on this, which is basically a 2-day course on how to build a whole model, where we teach a Scilab software, which is similar to a MATLAB software. There is no big difference as such, but it's more simpler and very easy to use also. And then on the day 2, we also teach the whole EV modeling, so that you can get the whole thing which you are trying to describe now, and also like you can get the graphs and things like that. Okay. So as a part of it now, we'll start ahead. As I was describing in my part of presentations, right? We start from the drive cycle, and then we go into calculating the wheel torque and the wheel speed as such. So let's see the model here and try to understand how we actually do this in the real vehicle. So we'll go to the chassis model, Bharat. So yeah, so which you see here that it's called Scilab for Rohit. So we're trying to give the data from the test cycle, right? So which is mentioned on the left hand topmost of it. So what we're trying to do, we are trying to feed the value of a Excel sheet. Bharat, can we open up the this one, side notes, and showcase on how it is seen? Uh, it's called SCILAB. S for sugar, C for. Okay. So if you could see here, this is the model data we are trying to feed. Bharat, can you double click and open this one, the Excel file? So this is a very complicated model, so it would take a while for you to build the model. As such as a data, so which you could see here that we are feeding. There are different drive cycles. We call NEDC drive cycle, WLTP drive cycle, FTP75. Depending upon each country, we have different type of drive cycles. Okay, so the one drive cycle which we're trying to showcase here is called as an NEDC drive cycle. So in the NEDC drive cycle, you can see here there's a timestamp. We are trying to take a value of a vehicle, the time, and then we are trying to measure the velocity at a given time. But can we plot a graph of velocity? So which you could showcase here that we are trying to take a data of the drive cycle, and we are able to uh, feed the drive cycle data. Like if you see here, this is the way actually the vehicle is trying to go through a pattern. Like if you take a real drive cycle, the vehicle will not go like this, right? The vehicle will be going more aggressively. It means that the vehicle speed will be continuously varying. And this is a very simple drive cycle. We call it as NEDC drive cycle, New European Drive Cycle. And in some cases, we use different drive cycles. For a vehicle manufacturer, they have possibly their own drive cycles, which they have collected, which is more realistic. Because if you try to design a vehicle using this drive cycle, it will consume lesser energy. But in the real vehicle, you will accelerate, decelerate quite faster, right? It means the vehicle will consume more energy as a part of it. So now if you see on the image, which is right here, this is a drive cycle. How we are trying to feed this value, we are trying to feed a value from the Excel sheet. So this data is there in the graph, is in the form of an Excel sheet, which is here on my left-hand part of the screen. We can close the screen, Bharat. We can just scroll down the values of the data there. So which you could see here, we have continuously logged the values. And you can also generate the drive cycle on your own. You can have some apps available in the internet for the paid price. They will be able to calculate all the acceleration, vehicle speed, and all these things, right? This is the way we have a data. So we have a data for 1180 seconds, and the plot of the graph is given like this. You can close this, Bharat. We can go back to the model. So yeah, we can go back to the, yeah. So now what we're trying to do is we're trying to feed that value of the vehicle speed. And that vehicle speed we're trying to convert from kmph. It is in kmph, it's kilometer per hour. We're trying to convert to meter per second. Then we are feeding the data to further. If you see here, there's a wheel speed and a wheel torque. In the inside of wheel speed, we can go to the wheel speed data. It is a very simple one. We can see through and do our calculations also. So if you could see here, this is a way we have done. There's a formula there also. V velocity divided by radius of the wheel into 2 pi by 60. Radius of the wheel, we know that's a constant, because for a specific vehicle we are trying to do, we would have imagined this is a specific wheel I'm going to use. So the radius of the wheel, then you have a constant parameter. We multiply, and we know the test cycle because we know the vehicle speed. We are trying to take a vehicle speed. We multiply that, then we'll get a wheel RPM. So now by this end of it, we are getting a wheel RPM of the wheel as such. We can close this, Bharat. We can go to the torque. Right. So the torque is a parameter of like how much torque has to be given to the wheel is always depends upon what forces it has to overcome. Right. Imagine there are two people sitting on the vehicle. It means there's more torque has to be at a wheel to move the vehicle. Right. So it means that you need to calculate the forces which are acting on the vehicle to calculate the torque of at the wheel as a part of it. So now we have seen here there is a rolling resistance and a grade resistance. Rolling resistance and grade resistance do not depend upon the vehicle speed. They do at a higher level of calculations, but will not neglect that parameter because the influence is very small. So we're trying to do calculations without taking a parameter of the vehicle speed. Wherever we say test cycle, it means that we are trying to feed the velocity of the vehicle to the model. And aerodynamic force, we know formula of aerodynamic forces, half rho a CD v square. So v is a velocity. It means if the vehicle speed increases, the velocity also doubles, because the way it has been put into a place is the equation. Again, deriving these equations is a very complicated thing, but as a simplicity, velocity increases, the aerodynamic force increases. It means higher the vehicle speed, it is the forces on the vehicle also keeps on increasing to higher numbers. It means that we need to have higher motor power to overcome the aerodynamic forces. That's why we're trying to feed the data into a vehicle aerodynamic model. We can just open the aerodynamic force model, Bharat. We will be able to visualize what is there inside the model. I believe it is all interesting for everybody and going well as of now. We can see here that we have done half, like this is a constant, then area of the vehicle, frontal area of the vehicle. Rho is the density of the air. Then CD is the drag coefficient, which is with respect to doing in aerodynamic studies, we'll get depending upon the shape and all these things, we'll get the CD value. Then V is the value, right? V is the velocity, but we want UV square because we need to multiply that, because in the formula we have V square. So we feed that value, then we multiply all this product information, like all the inputs, and we get an aerodynamic force. So we can close this, but this is a way we are able to do aerodynamic force calculations as a part of it. Then we have acceleration. Acceleration is F is equal to m into a, right? So m into a is Like A is acceleration again. So you have a mass of the vehicle, which we know as a constant. Then A is acceleration. So acceleration is, because we know rate of change of velocity, we can open up the a part of it, Bharat, acceleration part of it. So how do you calculate acceleration? dv by dt, right? So because you know the velocity with respect to time, because you have a plot which is you're trying to feed from the drive cycle. You have a test cycle, you feed the velocity, but you do a dv by dt, and then you will get that acceleration. Then you multiply the acceleration by GVM, not GVW. This is gross vehicle mass. Previously, we are doing a gross vehicle weight. So then we get the value, then we'll get acceleration forces. So by this, we are able to calculate the forces acting on the vehicle, right? Acceleration force acting on the vehicle. So here, what happens is, if you want to have a vehicle, let's say you have some vehicle like Ferrari or a Lamborghini, they go very fast. Within 0 to 60, they goes in, let's say, a few seconds. It means it requires like highest acceleration. If you require highest acceleration, again the forces on the wheel will be higher. That means end of the day, those forces has to be provided by the motor. It means motor size has to be it becomes bigger also in size. So acceleration becomes a very important parameter in vehicle sizing, the powertrain sizing. Because people say, right, like Ather, if you see, they say 0 to I think 40 in 3.9 seconds. If they tell 0 to 40 in 8 seconds, then the motor torque will be very lesser. But you have to beat the competition always, right? So that's why we would have those numbers and play around it. Acceleration becomes a very important parameter deciding the size of the motor as a part of it. So yeah, let's go ahead in the next part of it, Bharat. So we can close this part. Okay. And in the previous screen, we are able to see that we are taking all the forces acting on the vehicle, and we did a torque calculation. Okay, so by knowing the radius of the wheel, which is there on the top, we multiplied all these values. We summed all the values. Sorry, then we multiplied them together, and then we got a wheel torque. Right. So by this way, we can calculate the wheel torque itself, and we can close this, Bharat. So then when you do a wheel torque calculation, that's where it is all ending. We can close this part of it there, and we can go to the next one. So now with the model of the chassis, so what we have wheel speed and a wheel torque. That is the data which we could be able to generate from by having a drive cycle doing certain parameter of the vehicle. We go to a transmission model. We can go to a transmission model part of it. What we're trying to do in the transmission model, because we know the gear ratios of the transmission, very specific gear ratios, we know the efficiency of the transmission. So by taking these values and by knowing the gear ratios, the formulas are also defined right over there. By taking the values of the wheel speed and the wheel torque, we will be able to calculate the motor torque and the motor speed as a requirement. So we can close this, Bharat. So I believe this is able to give you the insights on how you can calculate the component sizing. Okay, so now the thing is, like, the next thing is the motor. The motor is a very complex thing which is there as a whole model. Because of certain confidentialities, it's not something we could just showcase to you. But as a learning scope of it, like, we have built certain parameters. Let's say if you're from a background of electrical engineering, and you're able to understand there are a lot of constants of the motor, there are specific efficiencies of the motor, and including all these parameters, we are able to build a whole motor model. We're able to feed the values of motor torque and a motor speed, and then by performing a lot of calculations, and also like by where I told about efficiency of the motor, by having certain graphs, you can feed that, and the efficiency of the motor varies with respect to temperature. The efficiency of the motor varies with respect to RPM and the torque. By including all the parameters of that, we are able to calculate the motor power, which is there on the side here. So we started from the chassis model, and let's say we have then we came to a transmission, then we came to a motor. So imagine we don't have a transmission. For cases we have a hub motor, right? So hub motor is like, well, the motor will be within the wheel itself, correct? So at that time we don't need a transmission. So that time the transmission will be neglected, and then the wheel torque and the wheel speed becomes a motor torque and a motor speed. If you do not have a transmission, like practically telling, it becomes very difficult to size the motor. The motor become very big in size, and that's why you don't have hub motors for a car application. Like Even there might have been 1 or 2 cases. They're at only the not at a production scale. But if you see any vehicle which has been manufactured in India or also in other countries, none of the hub motors are there for the car applications, because it becomes a difficult to package the motor. And second thing is it becomes like vehicle dynamic parameter, because you're adding a mass into the rotating wheel. And when you hit a hump, the suspension will not settle down very faster. There's a lot of inertia in the wheel. There are a lot of problems with respect to that. So for a simple applications like motor of 250 watt up to like 2 kilowatt, 2.5 kilowatt, 3 kilowatt, people are using the motors in the hub motors itself. But going higher, you definitely need a transmission in the vehicles as a requirement. So then that's what happens with the motor. By having the data, we can calculate a motor power as an output of it. Then from the output of the motor, we will give it to the battery. And inside the battery pack, we'll be able to model. Bharat, can you open up the battery pack? So we will slightly showcase on how exactly this, things are done and made into a place. It's a very complicated whole design as a part of it. Actually, this is what we teach in the today's course, which is going to happen in the next weekend. That is 6th and 7th of June. So where you can actually build the whole model itself. So coming back to the topic, where we are feeding the motor power, which you see in the left-hand side here, right? And then we're adding the motor and inverter and converter efficiencies. Like we're trying to multiply certain factor here without considering the complicated, I would say, efficiency models and all these things into place. With this, all the data we are able to actually, get deeper insights on calculating certain parameters, such as I would say the power supplied by the battery pack, and then other parameters such as like the battery current, which is here, and then there's other parameters such as the C rating of the battery pack, and on the other top of it, we can get number of cells. If you know the number of cells, it means you can calculate uh, the volume of the cell, volume of the battery pack, and you will be also able to do the what I say is a mass of the battery pack. Somebody was asking a question that how do we calculate the mass of the battery pack, right? You can calculate the mass of the battery pack because if you know the number of cells, because we know the power. By the power, we can do a lot of calculations, and then we'll be able to identify what is exactly required, and we should be able to actually calculate the whole components of it. The other side, we have a lot of calculations as a part of it. We can define like selected battery capacity and the cell capacity. Defining a lot of parameters, we'll be able to know even the volume of the cell, which is volume of the battery pack. We can even define the mass of the battery pack, total number of cells. Like this gives us a complete data of a whole way that we can be able to simulate and get a data of what can really happen in the realistic condition. You can close this, Bharat. So what this model gives you understanding is, I know it is not that it's a 10 hours course to actually teach about whole this thing. The importance is like, if you know the real importance of modeling now as a part of it, like, what you can actually and why the modeling is really required in electric vehicles. You can emphasize and you can bring out an importance of this modeling approaches. So with this studies, like the simple models and the complicated models of depending upon the data we have, we will be able to generate some results as a part of it. But can we run the simulation and we'll be able to showcase some of the graphs as a part of it? Yeah. So when we run the simulation, so if you can see here on the screen, which is shown to you, we have done the simulation of the whole electric vehicle powertrain. And then we are able to, but can we put across all the values of the chassis model? I'll take up the questions definitely just in a few minutes. So you'll be able to get all the graphs like this when you perform a simulation. And with these graphs, you're able to actually validate what are the kind of forces acting on the vehicle and what is the magnitude of all these forces which are acting on the vehicle also, right? So you can see here that aerodynamic force which is there on the vehicle, Like you could see how the aerodynamic force is continuously varying with respect to time and because of the velocity changes. Then on the other side, you can also see the acceleration forces. There is a negative acceleration. It means that it's actually the vehicle is like decelerating as a part of it. So now we know the acceleration forces. That's a very important detail about acceleration forces, that if you drive the vehicle too aggressively, it means like if you drive the vehicle suddenly increasing the accelerator, decreasing the accelerator and all, it means you're trying to draw too much of current suddenly out of the battery pack, right? If you take a racing application as a part of it, right? So that time the vehicle model actually giving us the information with the drive cycle. We can actually calculate what would be these acceleration parameters, because if you accelerate too hardly, then obviously the motor has to give a lot of torque at a given time. It is going to draw a lot of current out of the battery pack, and these will impact the whole battery pack life and all these things. And there's a lot of studies which we can also do as an outcome of this whole acceleration force identification. If you see on the bottom, we have a rolling resistance and a grid resistance. As of now, rolling resistance, it's become constant because it is not a parameter of a velocity, right? And on the other side, the gradient force is constant. It's zero basically because we did not consider any gradient angles like a theta angles. That's why the gradient force is constant. So then we can close these things, Bharat, and we can go and emphasize more on I think, the motor torque and the wheel torque and the motor torque and the wheel speed and the motor speed. So this is a way you're able to emphasize and study, and for any engineer at any requirement, maybe it doesn't depend upon which department of engineering which you study in, because when you perform these models, you're able to define, okay, what is a motor torque required, what is a motor speed required. I'll also have a small part of my presentation where I'll be able to showcase that how you're able to actually relate different departments of engineering and bring them together here, and why it is this is like a plant model. This is required for all the learners, because from here only we can segregate and tell, okay, how much is a motor current and all these things, if you're studying in a motor, if you're studying in a batteries and things like that, right? Let me come back here and try to get it here that wheel speed. So if you see the wheel speed here, which we're trying to calculate and measure, we're getting to know, because of the vehicle speed, what would be the wheel RPM, or rotation of the wheel as a part of it at a given moment of time. You can see here that how the the wheel speed is continuously varying with respect to a drive cycle data, right? So like there's a vehicle up to maximum speed is around 1400. So with this, we are able to understand, okay, 1400 RPM, if the vehicle is rotating, then the vehicle is going to reach the 80 kmph speed. Then we have a wheel torque, which is in the bottom side, left hand bottom side of the screen, where we are able to see up to 45, 50 Newton meter of a torque at a peak of the requirements, right? If you are from electrical background, you can relate the peak torque requirements of the motor and the nominal torque requirements of the motor, right? So by having this data, you're able to see, okay, the motor if I'm selecting should have a peak torque of, let's say, around 50 Newton meter, nearly around 55 Newton meter as a requirement. By maximize the screen, Bharat, you can be able to visualize more deeper, right? So if I can try to annotate, I won't be able to annotate. Bharat, can you take a screen and point out the nominal torque regions and the peak torque regions? So perfect, yeah, yes. Yeah. So anything which is happening below that region, right? Let's say 30-35 Newton meter, it is becoming a nominal, under that line, it is all becoming like a nominal region. But above it will be a peak. It's not exactly like that, but you can visualize, it gives you an understanding that, what should be a motor size. Like when you're selecting a motor, they have a data, right? Motor manufacturer will have a data. It's peak torque, it's nominal torque, and all these parameters. By having the model which is given to us here, it will be able to help us out to understand what would be the right selection. Let's say right now you're not just talking about wheel torque, it is not a motor torque, but if you have a hub motor, then this will be a motor torque also, right? We can close this, we can go to the next one. So now if you see here that by the data what we have, we get a motor torque and a motor speed. So now, because this transmission is there, right? If you have observed the motor torque graph in the wheel torque was peaking out at somewhere 45, 48 Newton meter, right? So if you see here on the motor torque, can you maximize the screen, Bharat? So if you see here that because of a transmission, we are able to reduce the torque at the motor, like because this is a Aether model, it is around 7.8 is to 1 is the gear ratio, 7.8 is to 1, yeah. So you can see right here that the peak torque has been come down drastically, right? It is like somewhere between 7.5 Newton meter of a peak torque, and then it is coming still below that. The nominal torque region is somewhere like 5 Newton meter. So if you have a motor which is having a 5 Newton meter of nominal torque, this can actually satisfy your vehicle requirements to achieve the acceleration and all these things with respect to the drive cycle which you're going to have, right? So then the peak torque also we will be able to decide upon and select the motor for a right sizing needful into a place. So this is a way you can actually decide what is the exact size of the motor torque, what is the exact size of the wheel speed. You should be able to decide. I can close this, Bharat. We can go to the wheel speed. So if you see the motor speed, which is here, like the motor is going, sorry, this is a wheel speed. The motor speed is going up to like 11,000 RPM, and it is in the regions of up to like, maximum it is operating somewhere around 7,000. So with this data, you can actually like, plot your efficiency graph, right? In the efficiency graph, you can like make a markings that you can see where the motor is operating at a maximum amount of time, right? And that will give you, okay, this is a region where my efficiency of the motor has to be very, very high, and I want my motor to operate in this region at major times. So when you do that, it means that you're actually tuning your transmission. If you tune the transmission perfectly, then that efficiency is always achieved, and you have a best energy efficiency in the system. So it means it consumes a lesser energy as a requirement. We can close this, Bharat. And then, yeah, so that's the way we are able to calculate a lot of different parameters. We can just plot in few parameters of SOC, Bharat, and let it be there. It's okay. SOC you can plot. So then few of the graphs of a cell current and all these things. Yeah. So what is the meaning of SOC? Where somebody was asking. SOC is state of charge. It means that how much of energy which is there in the battery pack, right? And the simplest meaning as a part of it. So it means that when you're driving a vehicle, it is consuming the energy, right? So how the energy is keep on consumed, and it reaches to a pace there is no energy in the battery pack. So that it means that the battery is 0% associated. It's like your mobile, the battery which showcases on the top of the screen, right? How much of the battery is left in the mobile. The same way in the vehicle also, if you see here that by doing a simulation, we're able to predict. Actually, this simulation data we have run it for 11,000 seconds, right? So I think close around. Bharat, what is this one? Drive cycle length, maybe 12 kilometers nearly, 12.8 kilometers in the FTP 75. So it means we have ran the cycle multiple times. And by doing that, we are able to actually, 12.8 kilometers, we will run the model if you run the model for a one time. So we have put the multiple number of drive cycles. You can see actually that, how the SOC is dropping, right? Then if you include a regenerative current, it means that now the SOC will not drop to 10%. Possibly the SOC will be still there at 25%. This will be able to do by implementing all this advanced optimization studies as a part of it. Then the bottom we have a battery current. Now you know what will be a peak current of the battery. As I was telling right in the past, you will be able to actually decide the conductor selections. Like this is 100 amps of current is going to the battery pack, and you can even keep a safety margin of another 50 amps. So let's say 150 amps is a peak requirement of the system. It means that you can select your components, select the conductors, and all the components as a part of it. That's what this model emphasizes, and it also very deeper in understanding the battery currents, which again relates to a C rating of the battery pack, which means it's a very vital information as a C rating because that defines how the battery is actually operating in wind regions. If you operate at higher C rates, it produces an enormous amount of current. There are a lot of problems with the battery itself. Okay, not for the racing applications because you use the battery for 1 year, 2 years, then you buy a new battery, right? But for the automotive application, you have to have a battery for a very long time. So then it means that it need to be operated at its limits, right? If you imagine if you abuse your mobile, like always playing the game, the battery will not come for a longer time, right? The same way the vehicle also, if you're abusing the vehicle very badly, it means you're operating a battery out of its C rating, higher C rates always, then the battery is going to go down its life. That's what we can study in detail and decide, okay, at any given time, what is the C rating of the battery it is operating. If you know what is the capacity of the ability of the battery to take a C rating, You can limit the battery always within those limits and ensure that battery is always operated within its safer seating limits. Then we have all the data which is here on the power supplied by a battery. Uh, like you could decide upon the battery pack sizing by knowing, typically if you see observe here, you can universally define, but can you maximize the power, battery power, this one. Yeah, you could see and emphasize here that how you are able to actually see the whole thing. If you decide upon yourself, then you can tell that maybe 2.5 kilowatt battery pack would be ideal for the for this bike, right? If you see in the Aether, it is around 2.4 kilowatt battery pack, right? So it means that we are able to have a data, because Aether haven't given us a motor data or cell data, right? But still having certain values assumed and having values considered as thumb rule with our experience, we are able to calculate a data which is more accurate and coming very realistic into a place, right? And same way you're also able to do the simulation and for your vehicle applications and things like that, and you could be able to get a data as a part of it. So this is in overall, as a part of it, what the simulation model would be able to give you basic insights. I believe it was giving clarity of how my theory session, of a practical session of demonstrating, because as I said, building a whole vehicle model is like a 2-day session. So I mean, I hope it kind of gave you clarity, right? So now what I'll do, I'll just go back to my presentation. But you can stop the screen sharing. I'll go back to the presentations and I'll be able to share my presentation screen and emphasize on some more parameters of the modeling. I'll quickly run through a few more things. I believe that gives you sort of an idea of how the modeling and why the modeling is important, how we do a modeling, and emphasis of modeling and things like that. So, right. So with that part of it, I will come to the next things. But modeling is not just about vehicle modeling, and there are subsystem models also, which we need to model, and why the importance of those subsystem models also. So, few questions here near how we can get a certificate. Yeah, certificate we will issue through online. It's a e-certificate which will be issued. We will discuss at the last part of the course. So if you see a subsystem simulation and a cell pack, now what we have showed to till now is only the powertrain simulation. It means if you want to decide the size of the battery pack, size of the motor, component selection, all these things, then you do that model, right? Now that is a one level of learning. Now the next level is, now if we want to model the cell, I mean, you need to study how the cell is actually behaves with respect to the life cycle, right? We did not study all these things because again, the cell will typically behave its own characteristics with respect to its life, with respect to its parameters, such as the temperature and the way we abuse the cell, like a lot of parameters as a part of it. So when we are doing the way we even charge the battery as in the consideration. So now we could actually have a advanced model. This is a model completely out of the, I would say, powertrain modeling. But this will be a modeling specifically. We do a cell level modeling. Okay. So in the cell level modeling, we will be able to implement a lot of other parameters such as cell degradation, SCF formation, capacity fading, power fading. Like, to understand all these things, we can implement a very different advanced models, and we'll be able to study how the resistance of the cell is increasing over the lifespan. Because if the resistance is increasing, then it won't be able to give out the current. Then there will be a reduction of the power. Then there are a lot of challenges in terms of lithium losses and corrosion of anode and a cathode, and like loss of electrolyte, formation of SCI layer. Like this, it's a very complex chemistry level understanding. With that understanding, actually, we build a cell level models. Okay. Then there is another complexity of modeling cells itself in another way. So what I mean to tell is there's a different division where there are engineers working in cell modeling. Why you do cell modeling as a reason is because something like this is cell models. Because you take a cell, you're going to use that cell for a 5 to 6 years or 10 years in the vehicle. If you want to tell to the customer what happens at the 6th year, let's say, I mean in the physical terms, it's like when he has purchased the vehicle, it is giving him 100 kilometers in the first 6 months. But after 6 months, maybe it is only giving him 80 kilometers because the capacity of the battery pack has been reduced. It means the energy capability, storing capability of the battery pack might have been reduced. By end of 5th year, it has been drastically reduced a lot, right? But how do we predict whether it happens in fifth year, whether it happens in fourth year, whether it happens in third year? How much does it happen? What parameters are really influencing this battery pack or a cell? All these things we are able to study only when we do a modeling. Because if you take a cell and study it for 5 years, it will take a long time, right? And by the time there are so many vehicles in the market already, which is beating the competition, you won't be able to do that. That's a way we will do actually the cell level modeling, and we will be able to study and run the simulations for, let's say, like many seconds, and check how the cell will behave, and we can improvise a cell model. And actually, when you improvise a cell model, you can implement into a BMS model, which is I'm showcasing here on my screen. And you can implement it to the BMS, and then BMS can be studied, for its lot of parameters. The algorithms can be developed by using the cell model. And this is actually industry approach, the way people do a embedded, I would say, coding for the BMSs, like what we say algorithm developments, right? They build a model in MATLAB. They can export that whole model into a C code by using a tools like a MATLAB embed and things like that. So that's when they can implement it to the BMS, and they can study all the parameters as a part of it. It means the simulation is not just a vehicle simulation. The simulation is also extended in these areas also. Okay. It means I'm trying to emphasize how much importance of simulation is there. And then even in motor controllers also, we can develop all the motor controller algorithms in the MATLAB, and we'll be able to implement it in the controller and test them even without having a hardware. And with having a hardware, you can do a HIL testing and things like that. So if you totally understand as a overall part of it, why do we perform simulation? Simulation saves a lot of time for us because we can't afford to have that much of time in real-time testing. Even though real-time testing is accurate, more accurate, but the problem is the time it takes and the amount of money it takes, right? So that will be not possible. So we have to go for adoption of a simulation approaches to study the parameters and advance very faster as possible. Can we? So you can run many test cases. Like, if you want to run a test cases for the cell, it means you need to have a cell that it is going to cost. There are a lot of dangers also. You need to have equipment. You need to have a lab technician. So many things are there, right? But with the simulation, you can just run it without having that hardware and all these things. So, and you can run many cases. Even if something wrong parameter if we set also, nothing will happen to the battery pack because it's simulation model, right? Then it's a quicker time to market. That is very important for OEMs and also driven time to suppliers. End of the day, it saves a lot of money. If you put across all these things, it is not just a vehicle modeling. The engineers are required at every level of a cell modeling, a motor controller modeling, DC-DC converter modeling, even charger modeling, like vehicle grid modeling. It means that the modeling is the first step every industry starts at, and that's how much the importance of modeling simulation softwares and the tools are there at the requirements of the industry. And that's where I could bring out to a small part of the conclusion, which I could tell, like, why simulation is so important and why you engineers have to learn about simulation and also like advance yourself in the areas of simulations too. Which Decibels definitely helps. There are a lot of courses which Decibels offers. I will share it on email, which is for you and which is happening this weekend and also in the upcoming weeks. If you're interested, you can definitely participate into it. So I'll come to a few more slides of this presentation. So I just conclude it by having here. The thing is, the course participation certificate, the course which you attended is free. There is no charge for that, as you all know. The certificate, there is a process for us to issue certificates. So there's a cost for it, which is already mentioned for all of you in the thing of it, which anybody who have participated in. So you will receive a course completion certificate by emails within a couple of days. I would say within Tuesday itself, you will receive the course participation certificate to your email address. If somebody wishes to receive certificates, we will provide you the link. You can make payments for that, and they should be able to receive certificates for the course participation, which we feel that it is more liberal that anybody can learn and explore, even spending without a rupee. So on the other side, at the last, so that's the thanks a lot for participating in the whole session. I believe it has brought you some level of clarity on why we do simulation and importance of simulation, and some technical insights on how we approach simulation, and some doubts might have been cleared and clarified. And that's my email address, which is suraj@decibelslab.com. We'll take some questions now here from now on. So you can contact me and you can write me an email. I tend to reply back as much faster as possible. It's not only for the course registration. You can contact me for some other things also, like directions. That's our website, which is lms.decimalslab.com. You can definitely visit our website, and you should be able to take up the courses and take part in the learning activities, which will be emphasizing on various areas of the electric vehicle powertrains and various areas of system level modeling and things like that. So I would showcase to you some of the courses, because somebody was asking where these courses are, which will be right here onto my screen. If you visit our website, so all the courses which are here available here. The live courses, there's an upcoming course by this weekend, which is on 6th and 7th. You can take part in that course, which is about electric vehicle simulation and modeling. We were teaching the whole model. Actually, we showcase to you with the Scilab software. We teach you the Scilab software on one day, which is Saturday, and we'll teach you the EV modeling on the Sunday. So it's a hands-on. The team size is limited to only 30 people, so that they can interact with the trainer, you can clear your doubts and things like that. And this is a course which I've attended, and then this is other course which is coming up for the learners about a 4 week span. We were teaching cell modeling and also the BMS modeling, and the vehicle modeling is also included as a part of it, which is a very advanced course at very affordable prices. This is a course which is starting from tomorrow, which is there on the electric vehicle subsystem fundamentals. You can definitely participate. We'll share it on email because you're alumni of the Decibels right now. We'll give you the coupon codes, so you could apply coupon codes, and you should be able to avail some discounts and participate in the courses also. So overall, we're trying to ensure that you will learn as best as possible, and you'll start your career in the electric vehicle industry. It's not just because we want to do it. It's actually the industry needs, and the country needs electric vehicle engineers to work in the sector and to make the system improvised. So by end of it, I will conclude my part of the session. Okay. If you have any questions, we can take up the questions here on the chat boxes. I'll be able to respond back to them now. So let's move on to the Q&A session. So somebody who have done with the session, that's most of the session which we want to deliver. Thanks a lot and for joining to the session, and we really appreciate you taking up all your time and making up your decisions to take part in the course. I believe we have made honest efforts to share our knowledge. I feel I believe it has brought you, I would say, like a time spending worth to learn about EV powertrain and get your exposure to simulation and modeling. I'm sure this is a very small part of it, what we have started today. But upon your interest, you can always pursue your passion and continue ahead. And Decibels is always there to help you for any of your learning requirements. You can always connect back to our team and let us know if any of your feedbacks are there. We'll share you the feedback form. Kindly share the feedbacks in the feedback form. And thanks a lot again for joining in. So we look forward to being in touch with you. We look forward to always be sharing our knowledge and keep inform you about EVs and help a country to get better engineers, help country to get better, help industries to get better engineers, and by the way, we all prosper to build a better sustainable mobility solutions in our country. Thanks a lot, everybody, and really appreciate you participating in the session. And people who don't have questions, you can exit from the session. And people who have questions, we can take up the questions and we can discuss it ahead. And thanks a lot for people who are leaving, and have a great time and stay safe and keep learning about EVs. Let's take some questions here for today's discussions. So kindly drop in the questions if you have any questions right here. So we are waiting for questions. Okay, so I'll go first on the YouTube live to take some questions. Okay, so thanks a lot for everybody for joining. May I know result accuracy? It totally depends what type of model you want to build. What is the purpose to talk about accuracy? I would say like typically we have 10% variations as of now. We could improvise it by having more mature data. So yeah, may I know how I may how has connection been established from the battery directly to the motor? Or was it told the AC motors was employed at a drive section? No, I couldn't get it, Ms. Jansi, that on the question. How battery directly to the motor? Um, Simulation session was much integrating. Okay. Minal, you can connect back to me. Maybe we can discuss on curriculum part of it. 850 cells. Okay. FOC is basically the field orientation control. I'm just going through the chat boxes. Looks like yeah. Somebody wanted to contact me on the further discussion, so I shared my email ID here, which is visible that desuraj@decibelslab.com. You can always drop me the details. Um, okay, so looks like that's a very general questions on the chat boxes here. How much energy generated during regenerative braking? Say it depends upon vehicle. It depends upon a lot of parameters, drive cycles, and all these things. Um, Yeah, Deep, as we discussed, the fees was there in the link. We will share it across to you if you would like to take part in there. Okay, so I'll take up a few questions from the Zoom chat box here. Okay, there are a lot of questions. Can we use fuel cells or ultra capacitors instead of batteries, which means the more efficient? As of now, fuel cell technology is not really, like I would say, economical, and also the hydrogen itself is not available right now. Maybe it takes some time. Uh, Mapping technique used for modeling of controllers. I think we can connect back to me, Salil. Maybe we can discuss more on that. Um, all right. So we have to go from chassis to battery, or should we start from batteries to chassis? Ritesh, there are different approaches of modeling. The one model which we have approached is the from the model of chassis to the batteries. Are the gear ratios given on the data sheet? Typically, it is given most of the time, Samprada. Um, Ritesh, how do we get certificate? You get certificate to the email. How much weight can lifted electric bike? Suppose that is a very specific question. Yep, the certificates will be sent over there. We are in the process to setting up a lab in our college, sponsored by. Definitely, Pradeep, we should be able to support you for that 100% requirements. For complete smaller to a very bigger scale, we could be definitely able to do it. You can connect back to me. That's my email address there on suraj@decibelslab.com. So we can definitely support you to set up labs at your favorite places too. Is there a community to intern with Decibels Lab? Yeah, definitely. You can connect back to me, Suryadeep. We can be able to support you on the internships also as well. Um, Thank you, everybody. We've been appreciating it. Thanks a lot. Ritesh, it depends upon. It doesn't matter which software. You could start with Scilab or a MATLAB, depending upon whom do you learn from. How affordable you can learn from. So that's all it matters. Because tool is a tool, you should be able to practice it. Thanks a lot, Salil. I really appreciate that. Okay, so that's pretty much, I think, all the questions still here. But the theory calculations will be also covered. Yes, Kishit, the theory will be also covered in um, the upcoming courses, which is there in the next weekend. Okay, so any other questions? I'm really sorry if somebody wasn't being touch based on the questions. Please do write me an email. I should be able to get back to you, and I should be able to support you at any given time. Okay, so never find difficult to reach me. So I shared my email address, which is there on my screen, which is suraj@decibelslab.com. You can always connect back to me, and at any time we should be able to support you on the emails or on the calls. Yes, there are courses which you can take it up. Uh, Real-time driving cycles, there are data available. You can download a lot of places, but you can generate your own drive cycles too. Is there any adverse effect due to heater and cooler on battery? It's not an adverse effect if the system is designed sort of that could definitely perform really good. There is no issues as such. Sampath, yes, we have vehicle models where you can just correlate the data and check and see how they perform together into a place. Uh, Drive cycle only depends upon V and T. That's how the representation of drive cycle is. And we also consider certain parameters of grade in few cases in drive cycles. What's the safety in EV vehicle? I think it will not be the question which I can answer. All right. So I'm really thankful for everybody to take part in this session, and it was great to host everybody at today's session. I believe it was worth spending time again. I believe I have tried to answer as much as questions as possible. I know it's not something I can always address everything because as a time limitations and stuff like that. So never mind. You can always connect back to Decibels at any given time. We could be able to support you, and Decibels is definitely happy to always um, create some more free courses, and we're working on that. We should be able to share you more and more and more. We are happy to support as many learners and create as many engineers as possible to the industry and also for requirement in the country. By that, I think I would end my presentation here and end the discussions here. And thanks a lot for everybody for joining in for today's session. It was a privilege to host you, and it was a privilege to have you here today on the session. And I wish you all the best for your career. And be in touch as always. And follow us on Instagram, follow us on YouTube, and connect with us at any places. We always share you something which is best, which is required for everybody. Yeah. Thanks a lot, and take care. Good night.